Our next section of material is 4.2. We're going to take a look at prime and composite numbers. And to start with, we're going to define exactly what we mean by those words. And I know you've seen them before, obviously, but just as a reminder, there is a component of this that sometimes catches people off guard. So we'll take a look at that. So to start with, prime numbers are any positive integers with exactly two distinct positive divisors. And a composite number is any positive integer with more than two distinct positive divisors. So let me pause right there before I keep going to the next pieces. Can somebody give me a prime number? What was it? 17, sure. Another prime number. 3. What else? 9 is not prime. 19 is prime, yeah. 9 would be composite, so we'll put that in our composite list. It's okay. What's another composite number, you know? 6 would be composite. 24, okay. So in each one of these cases, on the top, the prime numbers, the only divisors are themselves and 1. But in my second list, while they are divisible by themselves and 1, they're also divisible by something else. For example, the number 9, it's divisible by 1 and 9, and also 3, okay? There is a number that is neither prime nor composite. Not 0, we're only looking at positive integers, so it's not really in the topic of conversation. 1. 1 doesn't fit into either of these descriptions because 1 does not have two distinct factors. What is 1 divisible by? Just 1, right? It doesn't have a pair like all the other numbers do. So it's not prime. But if you look at the composite definition, it's supposed to have more than 2 factors to be composite, and it certainly doesn't have that either. So the number 1 is neither prime nor composite, all right? And that's actually a really important fact that we don't think of as being super important until we get down a little further in this lesson, and I'll show you why it matters. So what we're going to be doing is factoring things. Factorization is any expression of a number in factored form. Any expression. So for example, 24 has factorization that's 12 times 2 and 4 times 6. It has lots of factorizations. Okay, and 8 times 3. And 24 times 1. It has all of those. But there is a prime factorization as well. And prime factorization is a factorization containing only prime numbers. And none of those numbers that I just put up there, none of these pairs here, include only prime numbers, do they? They actually don't. None of those are prime factorizations. Some of them have a prime number in them, but they don't have only prime numbers in them. So prime factorization is reducing it to its smallest components, right? And finding out what those factors are. And what we're going to spend the next bit of time doing is finding ways, there are 2 different ways I'm going to show you, of finding the prime factorization for numbers. So we're going to take a number, they're going to be kind of large, 23,660, and we want to find the prime factorization for it. Now, one of the ways that you commonly see in books and taught in classrooms are factor trees. So raise your hand if you know what I mean when I say a factor tree. I'm not going to make you do one right away, but do you know what I'm talking about? Okay, cool. That's very common. Occasionally I have someone who says I never did it that way. Prime factorization with factor trees has one of the nice features of you can start wherever you know. So for example, this ends in a 0. So I know it's going to be divisible by 10. So it's a really nice number to divide it by because I know that when it ends in 0. And then I would have 2,366. Now, neither of those numbers, the 10 or the 2366, is currently prime. So we keep going with both of the branches. The number 10 is divisible by what? 2 and 5. Now, this branch is done because 2 and 5 are prime. You with me? So I won't be doing anything more over on that side. So let's come back to 2366. 2366, maybe you know a number that divides it, and maybe you don't off the top of your head. So any thoughts as to what you might try? 2 is probably your most natural thing to try because it's even. Yeah. So even if you aren't sure what to do next, it's even. So we might as well try to divide by 2. And what is 2366 divided by 2? 1,183, which is no longer divisible by 2, right? Right. So is it prime? No. Do you know what it divides by? Okay, we know it doesn't divide by 2. What would we try next? It doesn't divide by 3? Okay. What's that? 7 works. And we don't have a rule for 7, so you just have to try it, right? You've got your calculator if you'd like and do it. What is 1183 divided by 7? 169. Ooh, 169. Is that a number you're familiar with? Maybe you are. Is anybody? It is. It's 13 squared. I believe at this point I have all primes at the end of every branch. Now here's the drawback to factor trees. The branches all ended at different places, and I have to make sure I collect all of the ends of the branches to have the right answer, right? So I need to be a little bit careful as I'm working so that I don't lose the end of a branch and accidentally lose one of my factors. So I circled all my factors in green. Usually, we would write the smallest one first. You don't have to, but it's a common thing to do. And how many 2's are there? There are 2, so I can write it as 2 squared. What's the next smallest prime number? 5. And how many 5's are there? Just 1. What's the next prime number? 7. And how many of those are there? Just 1. And then my last prime number is 13, and there are 2 of those. This is the prime factorization, which is unique for the number 23,660. I want to show you another way to do this, okay? If you like factor trees, use them. I'm fine with that. It doesn't bother me. But I do want you to see another option. And if you like this one, then use this one. 23,660. I'm going to use a division step ladder, if you will, or something like this. And what I want to do is I want to divide by the smallest prime number that goes into this, which would be the number 2. So if you grab your calculator, what is 23,660 divided by 2? 11,830, right. Is it still divisible by 2? It is, because it ends in 0. So what's 11,830 divided by 2? What was it? 5,915. Right. Okay, is it still divisible by 2? No. Is it divisible by 3? No, because if you add them together, they won't end up being something divisible by 3. I'm just working my way up the primes. Is it divisible by 5? Yep, it is. What is it if you get it divided by 5? 1,183. Now, I mean, at this point, we've seen that number, right? So you know that you know what numbers are next. But if you hadn't, you'd be back where you were on the previous problem, and you'd be trying some of those things. We've already tried and checked out on 2, 3, and 5, and 5 won't work. So the next one would be 7, if you're going to sort of an order of the numbers. And it did divide by 7, just because we've already experienced this, and we got 169, which we recognize then as 13 times 13. It's a little more restrictive. I have to divide by primes in this method. I don't have as much flexibility. But the benefit that I have is that at the end of the problem, I have all of my answers right here in line, and they're in order. And that's kind of friendly. So if I think about it from here, I very quickly can see I have 2 squared times 5 times 7 times 13 squared, instead of having to make sure that I'm careful at the end of my branches. So it's not a huge deal, but those are 2 different ways of doing the problem. Okay, let me show you another one. This problem is interesting because it kind of looks like it's already factored, and it is a little bit, right? I have some powers involved, but the bases that are here, they don't happen to be prime numbers, 16, 81, and 6. So I got to do something different. I need to factor it more. It is not in your best interest to multiply this huge, hairy, ugly number out and then try and factor. That would be super counterproductive. All right, it's already partially factored. Use what you have and move forward instead of moving backward. So what would we do? Well, let's just take the bases themselves and figure out what we have. I have 16. I'm going to use that same factorization that I just did before with the ladder, okay? 16 is divisible by 2 to give me 8, by 2 again to give me 4, and by 2 again to give me 2. So 16 is really already 2 to the 4th, which is also raised to the 4th. Are you with me? Try the same thing with 81. Smallest value that divides 81. What would it be? 3 it is, yeah. What's 81 divided by 3? It is 27. Can I still divide by 3? Yes, I can. And I would get 9. And if I try a couple more times, I get a couple more 3s. So I have 3 to the 4th, again to the 4th. That wouldn't have to happen, but it did in this one. Now, 6 is a little bit shorter. 6 is what? Yeah, it's 2 times 3. You probably don't need to write anything out like I just did to actually know that. You just know it, right? This is 2 times 3 to the 6th. So each of the individual pieces now at the bottom are factored into primes. I'm not done with the problem because I can simplify some here, but the prime part is finished. The part that's remaining is what we went in to do in the couple sections ago, where we combined the same bases and used exponent rules to figure out what the exponents would be for that base. So the first thing to realize is that when you have 2 to the 4th, what do you really have? 2 to the 16th, good job. You would multiply the exponents. And we have 3 also to the 16th. Now what about this 2 times 3 to the 6th business? Yeah, it's 2 to the 6th and 3 to the 6th. That's exactly right. So now what? We're so close to done. Yeah, we're going to add them. Well, I mean, we're going to combine them with addition on the exponents. What's 2 to the 16th times 2 to the 6th? 2 to what power? What was it? 22nd. And how'd you get 22nd, Cameron? Right. We add the exponents. And then how about the 3? It's 22nd as well because they were the same, actually matching as we went along. Okay. Every now and then I put a problem like this one on the test when I get there. And I have students have a lot of trouble with this. So much so that oftentimes if it's small enough to deal with, they will multiply it all out because they don't know what to do. Okay, so this problem involves a little bit of thinking about distribution in reverse. So if you take a look at the components of this, there is an addition symbol in the middle, right? So what I have is I have 2 separate terms separated by addition. And within each of those terms, there are some duplicate factors. What do they have in common? Well, they both have a base of 2, right? The first one has how many 2's? 2 2's. The second one has how many 2's? 4 2's. So how many 2's do they have in common? 2 2's. I'm going to leave a parenthesis here. How about 3's? They both have 3's in them, right? The first one has a 3 to the 5th, and the second one has a 3 to the 4th. So what do they have in common? 4 3's. And they both have a base of 7 as well. There are 55 sevens in the first number, and there are 55 sevens in the second number. So how many sevens do they have in common? 55 of them. So we have sort of pulled out what they have that match. But what remains are the things that they don't have, or the things that they have that don't match, I should say, separated with addition. There will always be addition in the second set of parentheses. It may be, like if, let's just say for instance, because I've had this happen, or maybe it's in your notes, or your homework rather, I mean, where it actually has one here that's 2 squared, 3 to the 4th, 7 to 55. It's everything I just pulled out. So if I pull everything out, what's left? Isn't that really loud? 1. Because this process of pulling it out is division. That's what factorization is. It's division. It's breaking it down into its multiplication pieces. And if I divided something by itself, I would have the number 1 left. Now, on this problem, we have more than just that left. So on the first piece, what have we pulled out? The 2 squared, so there's no more 2's. How about the other piece? There's a 3 left, right? I pulled out 4 of the 3's, but there are 5 of them, so there is still a 3 here. And what about my 7's? I pulled all those guys out. How about the second underlined piece? There's a 2 squared that's left. What about my 3's? We took care of them. And my 7's? We took care of them. So the last thing to do then is to simplify what's in parentheses and see if it is prime or if it's composite and needs to be factored further. What is 2 squared, 4, and then added to my 3? 7. So I have a 7 back here. So I don't need to simplify the 7, but what do I need to do? Yeah, I need to include it or combine it with the other 7. So this is 2 squared, 3 to the 4th, and 7 to the 56th. Any questions on that? All right, we will pick back up in this lesson when we come back on Monday.